Okay, there's a few people online. I'll go ahead and start. Okay, so number one, limit as x approaches 0. Root x plus 19 minus root 19 all over x. We know direct substitution is our first step. I'm looking for you to show me your direct substitution step, especially if it's approaching a real number. So plug 0 in, I get root 19 minus root 19, so 0 over 0. We know there's a hole, we know there's a limit, real number waiting for us, so we go through conjugate method, right? Right, so we can expand the numerator, but leave the denominator alone. Keep writing your limit notation. We just have to worry about the first pair and last pair. Combine like terms, 19 minus 19, that cancels out nicely to be 0. X's also cancel out. This is what we want. We want the wholes to cancel out. There's still a 1 left over in the numerator. Now we reevaluate. Direct substitution again, replacing the x with 0. One root 19 plus 1 root 19 will be 2 root 19. It's okay to leave your answer leaving radicals in the denominator. You don't have to rationalize your answer. Okay, number 2. Start off with direct substitution. Because we're approaching a real number. And -3 in for x, we get 0 over 0, which tells us that there's a hole. We can find the hole and remove it. So this is a pretty straightforward factoring problem. Multiplies to be -3, adds up to be 2, cost 3 and -1. X plus 3 above, x plus 3 below. We find the cause of the hole. We cancel the x plus 3 factors out. There's a 1 remaining up in the numerator. We reevaluate. Direct substitution, -3 in for x. So -3 minus 1 is -4. Careful that -4 is in the denominator, not in the numerator. So 1 over -4, -1/4. Right, number 3, limit as x approaches 2 from the left. We do see one-side limit, but we always want to start off by convincing ourselves that, so here, limit as x approaches 2 from the left, we're getting a a 0 over 0. This is a little bit different though, because this is an absolute value function. Typically 0 over 0 tells us that there's a whole, but something a little bit strange about absolute values. So we talked about yesterday how there's two ways that we can go about it. We can get the piecewise function or get the absolute value to be piecewise function, and then we can read the piecewise function, look at the one-sided limit, or we can graph it. So this is a very useful skill when we get down to later on this semester. Um, Derivatives and integrals, it is very helpful to understand that typically absolute value functions are kind of hard to work with, and it's easier to work with or think about if we can treat it like a piecewise function of two linear graphs. So if we step to the side here and say, okay, well, we know that absolute value of x minus 2 looks something like this. Basically, a vertex at x equals 2. And on either side of 2, we see there's a segment that is showing positive slope. And then to the left, there's a segment showing negative slope. So we know it's made up of two lines. We have one line segment that is the positive slope version is just the x minus 2, no changes, just drop the absolute value. And the positive slope is showing to the right of 2. So we say and then there is the negative slope version that is living to the left of 2. So we say negative parentheses x minus 2, and that's to the left of 2. The vertex is defined by both these functions, so we should have to put equal sign either above or below. It doesn't matter which one. Now, this is only showing the numerator. We want to show the entire expression, so we're going to divide by x minus 2 to the entire expression. And now this is equivalent to the cleaned up version of our piecewise. So x minus 2 over x minus 2, that's going to reduce to 1. And then negative parentheses x minus 2 over x minus 2 reduced to be negative 1. So we can now read this graph a little bit easier here. If we're approaching 2 from the left, that is, those are values slight less than 2 headed towards 2. And we see that the y value is holding steady at negative 1. So that's one way that we can say that the one-sided limit is equal to negative 1. Another way is we can sketch this graph and visually see that there's two horizontal lines here. One is y equals 1 to the right of 2, and the other is y equals negative 1. And if we are approaching 2 from the left, that means I'm picking a point to the left of 2, and I'm heading towards 2, and we can see that this arrow is headed towards 2, and the y value is holding steady at negative 1. Okay, number 4. Okay, number 4. All right, direct substitution first. Approaching a real number here. We're getting 0 for x. We get 1 over 1. 1 minus 1 is 0. 0 over 0. We know that there's a hole. We know that there's a limit waiting for us. We can't do anything with the denominator x, but this is offering a hint. We know that there must be an x hiding in this numerator portion that is causing the same issue as the denominator. So if we can step to the side and focus on trying to get these two combined to be one fraction, we're going to have an easier time identifying and removing the hole. So right now, the two fractions are not sharing a same common denominator. So create a common denominator by really just taking these and multiplying them. And these are, that 1 is really not affecting anything. So just x plus 1. No balance needed. This one is missing an x plus 1. Multiply at the top on x plus 1. Protect it with a set of parentheses because there's a minus sign that comes before it, which means we have to distribute that negative through. Numerator cancels out or combines to be just negative x because 1 minus 1 is 0. So now we have a more useful version of the initial numerator of our problem. So we're going to make a substitution back to our original problem. Okay, we're still looking at a complex fraction, but now if we can somehow bring that x up to the top, we can begin to see maybe these are what's that can cancel out. So this divided by x, the same thing as this multiplied by the reciprocal of x. Now it's easier to see where the fits, the pairing, and the canceling out will occur. There's a negative 1 that remains up top. Direct substitution, 0 for x. All this is in the denominator, so negative 1 over 1. I get negative. Okay, any questions here? All right, number 5. We have to switch gears a little bit here because now we're approaching infinity. So we know infinity, we don't do direct substitution. Okay, but rather we compare degrees. So we find the highest degrees in the numerator and denominator. Sometimes they may not be in order, so we have to search for them. And looks like my highest degrees are matching, degree 5, degree 5. So we know the limit is just the ratio of the coefficients. So 4 over 2. Number 6, maybe we know we got to compare degrees, but these are not different. These are not the same family of functions. And also, I'm going to see if I can rewrite it because that negative exponent, typically, it's easier to interpret an expression if I can work with a positive exponent. So I'm going to push that 3 to the denominator. And now I'm still approaching infinity, but I can't really compare degrees. But hopefully we can see that, oh, this is compared to growth rates. These are different families of functions that are directly above each other. We can identify each of them, and then also is approaching infinity. So think about comparative growth rates. Okay, so to review the relationship here, logs grows at the slowest rate, followed by radicals, followed by polynomial slash algebraic, and followed by exponentials. So x to the fifth, that falls under the polynomial category. 3 to the x falls into the exponential category. And we see that exponential is growing faster. My denominator is growing faster. And if my denominator is growing faster than my numerator, my overall fraction is getting smaller and smaller and smaller until it is headed towards 0. L is logs. Got logs, radicals, polynomials, exponentials.
So if it was faster or slower, you would test 100.
That's right. If it was, so let's do a variation of this problem. If it was limit as x approaches infinity, let's say if it was like 3 to the x over negative x to the fifth. Again, compare the growth rates. But the difference here is my exponential is above and my polynomial is below. So my numerator is getting larger and larger, faster than my denominator. So I know that my overall fraction is getting larger. So it's either going to go up to positive infinity or negative infinity, right? Depending on the signs. But we know that it's going to be growing without bound. And so we're going to test 100 to see which direction that we're headed. Because we already know we're down to 2 options. We just don't know what the signs are. So if I plug in 100, 3 to the infinity is still positive. 100 to the fifth is positive, but there's a negative in front. So positive or negative is negative, so negative infinity. And comparative growth rates only works if we're approaching infinity. If it's going to negative infinity, then we can't rely on this relationship. But if I give you comparative growth rates, I won't let it go to negative infinity. I'll let it go to infinity, and then it's either one of these 2 options, either 0 or a plus or minus infinity. Okay, number 7. First things first, we are always ignoring one-sided limit, right? We don't want to assume anything here. So we direct substitution first, -3 in for x. So here I'm going to get 12 over 0, and this is very telling because this is not indicating that there's a hole. There's a what here at x equals -3. There's a vertical asymptote, which means that normally the limit doesn't exist, but we notice that it's not asking for the full limit. It's only asking for the behavior of the graph as it approaches the vertical asymptote just from the left side. So we know that if we're approaching a vertical asymptote just from the left or from the right, there's only 2 options. Either the graph is doing this, going to positive infinity, or going down to infinity, right? We don't know which one. It's not both. It's got to be one of these. So now we can rely on decimals. The danger that students experience, that I see students experience, is they see that one-side limit and they automatically assume that it's dealing with testing decimals. But sometimes you may have a full limit problem that's disguised as one-side limit. So just be careful. If you see a one-side limit, sometimes it is there to distract you, right? So convince yourself that there's a vertical asymptote before you go and test for decimals, right? If you get a 0 over 0, then just go ahead and find the hole, remove it. There's that one side limit doesn't play a role. It's just there to throw you off, right? But in this case, we are getting vertical asymptote. We are doing one side limit. We know we're choosing between the two options because we're headed towards infinity. All right, so negative 3.1, and for x, we can do this without a calculator because we only care about the signs, so we don't have to find the actual decimal value, just the signs. Okay, so this is positive 9-ish plus 3. That's still positive. Negative 3.1 plus 3 is negative. Positive or negative is negative. So between these two options, we know we're going to be headed towards negative infinity. Approaching 1 from the right. Let's not assume anything. I'm always looking for you to show me your initial direct substitution step. So 1 for x. Four over 0. So now that is indicating that we do have vertical asymptote. So just like before, we can use decimals to confirm whether we're headed towards positive or negative infinity from the right side of 1. So we can test. Numerator will stay positive, denominator will stay positive, so positive infinity. Okay, next page, number 9. We have G, F, and H that are shown in this relationship here. You got lower, middle, and upper function. You have the upper and lower functions defined. It's just the middle function that's unknown, but we're trying to find the limit as x approaches negative 1 of that middle function. This is squeeze theorem. And so we should have to set everything up. Limit as x approaches negative 1 for each of our lower, middle, and upper function. We do have an upper and lower function to explicitly to work with. So we're going to copy that down and evaluate the limit, go through direct substitution for both. Plug negative 1 in for x. I get negative 1/4 plus 1/2 minus 9/4. That gives me negative 2. The middle will stay unresolved. And then to the right, we're approaching negative 1. So negative 1 in for x, that's sine of negative pi over 2. Sine negative pi over 2, that's same thing as sine of 3 pi over 2. So negative 1 is the result there. Negative 1 minus 1 is negative 2. I have negative 2's on both sides. The middle limit has no choice but to also share that same limit. So therefore, by squeeze theorem, we can conclude that the limit of that middle function is going to be equal to negative 2. And there's only two options. Either these are the same and you can conclude what the limit is. If these are not the same, then your limit is inconclusive.
Is that all you need to say for your justification?
Yeah. Yeah. Show your steps, and then you can make your conclusion. Yeah, this is basically your justification step. H of x. Yeah, sure. So we're going to plug in negative 1, right? So we have sine of negative pi over 2. And if you don't recognize negative pi over 2, because it's not inside your unit circle from 0 to 2 pi, you know you can always add 2 pi or subtract 2 pi to get it into the range that you can maybe recognize a little bit easier. So a variation of negative pi over 2, a co-terminal angle is by adding 2 pi. So negative pi over 2 plus 2 pi, same thing as plus 4 pi over 2. And then this becomes more recognizable, right? 3 pi over 2. So now sine of 3 pi over 2, we should be able to recognize this, that the unit circle value here is -1. And if this is -1, I also have a -1 that follows after that. So -1 minus 1 is -2. So there's my -2. All right, number 10. We have a function defined by f of x. We understand that this restriction is telling us that b as x is equal to -6. And this is talking about an ordered pair here. And then x doesn't equal to -6. That means to the left and to the right of -6, it's all relying on this function. So basically, this is where your connected graph is going to be. Okay, find the value of b such that f is continuous at x equals -6. So anytime I see the word continuity, I'm just going to step through continuity conditions. And I may ask you to show that your continuity steps. All right, so first step is, does the point exist? We know that the x value in question is -6. So -6 involves order pair with the second piecewise. So plug -6 in for, well, there's no variables to plug in, so it'll remain b. So my order pair, f of -6 equals b. Unresolved, I still don't know what b is, but we can keep going. Second statement, does limit exist? And if you look at your second condition, it's either evaluating the limit of an expression, or we have to do a split one-side limit, approaching, -6 from the left, approaching -6 from the right. But here you don't see a less than or greater than, which means that the less than and greater than are both contained within the first piecewise. So there's no need to write out two one-sided limit. You can, but you're just doing additional work. Let's just do the limit of that top expression, just write it out once. So I write out my expression, evaluating my limit as we approach a real number. Direct substitution is always our first step. We don't want to assume anything here, so we do direct substitution. We do get something that convinces us that there's a hole. The limit does exist. So then we reevaluate after we factor. So we factor the numerator, remove the hole, reevaluate, and we get a hole, we get a limit. It's -4. So the limit exists, and we keep going, right? Third condition, all we're doing with the third condition is going back to the first two, and we're just looking back at our data that we've found. And if we want the third condition to pass, because we are looking for, we're trying to promise continuity here. So we want all three conditions to pass. I want this condition to pass. I want f of -6 to equal to limit as x approaches -6 of f of x. And if we want to do that, then my b value has to be equal to -4 in order for that hole to get filled in. So b must be equal to -4. So we're not creating anything new. We're just following the continuity condition, and we want all three statements to be true. And in order for that to occur, we're able to solve for b without even really trying. We're just going through our conditions. Okay, 11 through 18, we're just reading the graph to either finding the limit, one-sided limit, or order pair. So approaching, finding the limit as x approaches 3, we know that there has to be a consistent approach in order for our limit to exist. So if we pick points on either side of 3 and head towards 3, we can tell that the arrows are headed towards the same y value. So therefore, limit is equal to 2. Number 12, approaching 1. So I want to approach 1 from both sides of 1. And if I pick points on either side of 1 and head towards 1, they're both pointing towards the same y value. They're both pointing towards the y value of 4. F of 3. F of 3, we're looking to see, is there any point that's defined when x equals 3? There's a hole, but hole doesn't show definition. and there's nothing else that's defined, so f of 3 is undefined. Okay, f of -2, we're looking up and down -2. Do we see any y value that is defined? The whole, we can ignore that, but there is a point that is defined here, so f of -2 is -2. Okay, we're looking for the full limit as x approaches 2. So if I pick points on either side of 2, draw arrows towards 2, they're both headed towards a y value of 3. So there's a consistent movement towards the same y value, so 3. Approaching -2 from the right side of -2. So I'm just picking a point on the right side of -2 and following the arrow. And I'm just looking at the behavior of that arrow. So that arrow is headed towards a y value of 2. We don't need to check the other side because it's only asking for the movement from that one arrow. F of 1, we're looking for an ordered pair that exists. F of 1 is 2. Limit as x approaches -2 from the left. Now we're looking from the other side of -2. So we pick a point on the left side of -2, draw an arrow, head towards -2. It's headed towards a y value of -2. So that's our one-sided limit. Okay, 19. We have a piecewise function. So as we evaluate limits in order pair, we have to make sure that we are picking the correct expression based off of the restrictions and where the graph exists. So part A, limit as x approaches -pi from the left side of -pi. So we know that they're not giving us the function. We have to find that piecewise. So to the left of -pi, we can smaller than -pi. We know that's going to be it's going to meet this criteria here. So we know we're working with sine of x, and so we just do direct substitution first, right? Ignore the one-side limit. The one-side limit here is helpful in the sense that it is telling us which direction that we're coming from. So if there's a split at that x value, that one-side limit does tell us whether to pick the one to the left or one to the right of that x value. So -pi goes in for x sine of -pi. If you don't recognize sine of -pi, you know you can always add 2pi to get to something that may fit better with your unit circle knowledge. So -pi plus 2pi is pi. So sine of pi, we should know that unit circle value is 0. Part B, approaching just -pi. Sorry, I did not include, or maybe it didn't come out too well. I meant for this to be -pi. Yeah, from the right. Yes, from the right.
If it was the way you had it, wouldn't it still just be 0?
You're right. Yes, that's a good point. So for part B, it's asking for the full limit. That's a good point. It's asking for the full limit, but you see that pi is split on either side. So we do need to test tangent to see if there is an agreement. So yeah, you're right. It is asking for the full limit, but we still need to look at the right side. So let's for part B. Yeah, this is not a typo. This is correct. But we do need to look at the limit as x approaches -pi from the right side of -pi. So if we do that, we know we have to, it's going to fulfill the condition for the second piecewise. So the limit as x approaches negative pi from the right side of negative pi. Even though it's not asking for the right side of negative pi, we are testing it because we do need to see, is there a common movement towards the same y value from both sides of negative pi. So negative pi from the right side of negative pi. So tangent of x, we do direct substitution first. Tangent of negative pi, we don't recognize it. That's the same thing as tangent of pi. If we add 2 pi to negative pi, we get pi. Tangent of pi is 0. So now we see that the one side limits are in agreement. From the left side of pi, it's headed towards y value 0. From the right side of pi, it's also headed towards 0. So we can therefore conclude that the full limit does exist, and it is equal to 0. For part C, limit as x approaches pi over 4. The issue is that we see pi over 4 as a dividing point where both sides of pi over 4 is showing a different piecewise function. So we can't just rely on one limit statement because we have different graphs on either side of pi over 4. So again, we're going to rely on one side of limits. So limit as x approaches pi over 4 from the left side of pi over 4 for tangent of x, and also limit as x approaches pi over 4 from the right side of pi over 4 of cosine of x. So direct substitution first. Tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. And we can clearly see that as we approach pi over 4, one y value is going to 1, the other y value is going to root 2 over 2, and those are not in agreement. The arrows are not pointing to the same y value, therefore the full limit would not exist. Part D is only asking for the ordered pair. The ordered pair is defined with the last piecewise because of the greater than or equal sign there. So pi over 4 goes in for x, goes down to pi over 4 is for 2 over 2. So that's our y value.
It's okay. Are you like just answering any questions?
Sure.
Okay, on page 10 in our BC packet, unit 1, on number 5, I was a little confused. I understand that it does not exist because they're both infinity, but wouldn't one of them be negative infinity for the limits?
Okay, sorry.
10.
Page 10.
Number,
Let's see.
in the, just like the
Oh, okay.
first
Original
packet, yeah.
packet.
You don't have to be approaching left or right for it to be positive and negative infinity. It's approaching whole number.
Oh, I was like testing it from both sides. Cause it has a vertical asymptote, so I was doing negative 6.1 for the left, and then that gives you a negative on the bottom. So
I
that
should
should,
just stop. It does not exist.
yeah, but I just remember like on the key, or when we did it in class, they both had infinity, so I was just,
Yeah, does not exist would be acceptable unless I ask you to subcategorize if possible. And if I'm asking you to subcategorize, then you would need to test -6 from the left and from the right and see if they're in agreement. If they're in agreement, then we can subcategorize it as possible.
okay, so like, but if we were talking about like -6 from the left,
Good morning, students. For a brief informational meeting on esports, please go by room
From your left, okay.
wouldn't it?
4207 to talk to Mr. Pop. If you're interested in esports, please head to room 4207.
How would the subcategory be infinity if? I don't know, because I was testing like -6.1.
Oh, right.
If you get a negative, so there wouldn't be.
36. Yeah, so numerator will be positive. Denominator is -6.1. Yes,
So infinity
You're right.
wouldn't even be a subcategory?
it wouldn't be a subcategory. If these, if
Okay.
these are different, then we will leave it as does not exist. Yeah, sorry about that. They're interchangeable. Yeah. Let's see, page 3, this is number 20. Number 20 says identify each type of discontinuity. So discontinuity can either be jump discontinuity, it could be vertical asymptote, it could be involving a hole. So if we factor everything out, it's a little bit easier to identify potential issues. And we're basically looking at the denominator. Whatever's in the denominator is going to be a potential issue. So if we factor everything out, x minus 5 remains in the denominator. So anything that remains in the denominator, you know that's going to be that is going to be related to your vertical asymptote. Any factors in the denominator cancels out, is giving you an indication where the hole is. So vertical asymptote at x equals 5, we know that is a non-removable discontinuity. We know there's a hole at -3. If we want to find the y value of that hole, you're going to plug -3 into the reduced expression, which is 1 over x minus 5. So if I plug -3 into 1 over x minus 5, I'm going to get -1/8. So that ordered pair is the hole, and a hole is considered a removable discontinuity.
I had another question on the original.
Mhm.
On page 31, on number 9, how do you know it's 0?
This one here.
Yes,
Yeah.
because I was thinking like they were the same degree, but is that not?
So if we think about the behavior of sine, okay, so sine looks like this. But it's always hovering between -1 and 1. And so it is, but it's basically like a really small number, right? But if you look at the denominator, if it's approaching infinity, is getting really, really large. Like, let's say like a million or a billion or whatever. So imagine like negative, 0.01 or 1 over a billion. That value is getting smaller and smaller. It is alternating signs, but it's headed towards 0 because that denominator is getting so large, and that numerator is just keeps hanging out around -1 and 1.
So
It's growing faster, and the numerator is really just it's a predictable number that's between -1 and 1, and over time, that huge number is going to overtake whatever changes occurring in the numerator, and it's going to head towards 0.
This goes on to the same thing. This goes on to the same.
That's what I say.
is there anything that's slower?
No. Yeah. So anything in the denominator, if it was like x or root x or natural log of x, it's all going to eventually overtake that sine of x. It'll all be 0.
So that would essentially be like the slowest option, sine or cosine.
Yes, but I don't think we don't consider sine and cosine as a growing function. It's an oscillating function. So it doesn't quite fit into comparative growth rates. We kind of have to think about it independently.
Okay.
Okay, number 21. Identify all horizontal asymptotes. Yes. Yes, you can get away with just the x value unless I specify give me order pair. So we'll, yeah. But yeah, if I don't specify it, then you can just give me the x value. Okay, identify all horizontal asymptotes. We know that this is one of those strange problems where, well, first, we know horizontal asymptotes rely on comparing degrees. And if we compare degrees, root x to the sixth power, that's really x to the 6 times 1/2, right? And which is really x to the third power. So we know that after we clean up that numerator, it does end up being the same degree. And if it's the same degree, we know that the asymptotes do exist, and it's going to be the ratio of the coefficients. However, we know we see radicals in play here, so we do need to consider that there's a possibility that there may be split asymptotes. So we do need to consider both the positive and the negative side. Normally, if you have just a normal rational function, and if the asymptote exists, there's not going to be split. But anytime you see a function that seems a little bit strange, we do need to test both sides and convince ourselves. If we approach positive infinity, it's just the ratio of the coefficients, so 4/5. But if we're headed towards negative infinity, the numerator is always staying positive, but the denominator is going to switch over to a negative. So positive over negative is negative. So our asymptotes are split. We have two lines on either side of infinity. But here's something to be careful about. It's asking for horizontal asymptotes, so make sure that you name the equation, y equals, not just 4/5 or negative 4/5. You got to name those two lines. Okay, 22, a bunch of piecewise functions. Part A, approaching negative infinity. So negative infinity, we know that is referring to the first piecewise because infinity is less than 2. And we know that if we're dealing with infinity, we don't plug any values in. We do compare degrees. Numerator and denominator share the same degree, so 1/2, just 1/2. Part B, we're approaching 2 from the left. 2 from the left, we know is living in that first piecewise there. So x plus 5 or 2x minus 4. We do direct substitution first. See what's going on. We see that there is a vertical asymptote. The limit does not exist, but then we go back and see, oh, it's only asking for the approach to the asymptote from the left side. So use a decimal value. 1.9 plus 5 over 2 times 1.9 minus 4. 1.9 plus 5 is a positive. 2 times 1.9 is going to be slightly less than 4, like 3 point something. 3 point something minus 4 is a negative. Positive or negative is negative, so therefore negative infinity. Remember, with infinity, we don't plug anything in. We compare degrees. It's horizontal asymptote, right? Yeah.
On number 23, how do we know that on the right side of the vertical asymptote that's approaching positive? Will they both go up? How do you know they both go up and one goes up and one does?
Okay, because this statement is subcategorizing for us. It's subcategorizing by saying the limit doesn't exist, but infinity indicates that both arrows must be going up. Yeah. So whenever we see this, we have to think of this as a subcategory. If it was does not exist, if it says does not exist, then you have some options. You can make it this, you can make it different directions, you can make it
Like F.
like F, right? If it's like F, you have a lot of options. Make it an asymptote, make the arrows go wherever you want, make it an endpoint, or make it a jump discontinuity. But if it's infinity, this is describing the behavior from both sides. We need both sides to show infinity. Okay, 2 from the right. 2 from the right, we're talking about the 2x minus 5. Remember, direct substitution is our first step. We don't want to let that one side limit throw us off. We always do direct substitution first. Plug 2 in for x. 4 minus 5 is -1. That's a real number. There's no need to do anything else, right? If the limit exists, there's no need to worry about any decimals. Remember, you only play with decimals if there's a vertical asymptote. Limit as x approaches 2. There is an order pair defined at 2, but we know order pair has no say on what the limit is. We're talking about the arrows here. And then the arrows are basically what we gather from parts B and C. And we see that they are not in agreement. They're not headed towards the same real number y value. Therefore, the limit does not exist. Approaching 5 from the left, that's going to be a number less than 5, approaching 5, so that's 2x minus 5. Direct substitution gives us a real number. No need to do anything with decimals. We've already found our limit. Part F, approaching 5 from the right. Because if I choose 1.9, for instance, 1.9 times 2 is a number slightly less than 4. 3 point something. So 3 point something minus 4 is good. Or negative. Okay, 5 from the right. So 5 from the right, we know that's talking about the last piecewise here. So we do direct substitution, convince ourselves what's going on here. Plug 5, we get negative 21 over 0. So that convinces us that there's a vertical asymptote. Normally the limit doesn't exist, but we're only approaching from the right side of 5. So we're going to be deciding between positive or negative infinity. So plug 5.1. Negative 5.1 squared plus 5, that's going to be a negative. 5 minus 5.1 is also negative, so 2 negatives make it positive. Okay, part G, limit as x approaches 5. We do have an ordered pair, but we know ordered pair has no say on the limit. We need to look at from the left and from the right of 5, and E and F gathers enough information for us to make a conclusion. So one side is headed towards 5, the other side is headed towards infinity. We don't see an agreement between those two sides, so therefore a limit doesn't exist. Approaching 3 from the right, we know that is referring to this piecewise. So plug 3 in, see what happens. We get a real number, so we stop. We have our limit, no need to do anything else. Approaching infinity, we know that is greater than 5, so we set that up. We know approaching infinity, we don't plug anything in, we compare degrees. Numerator is degree 2, denominator is degree 1. Numerator has a higher degree. We know this fraction is getting larger and larger, and it's only 2 options, either going towards positive or negative infinity. To decide between those two, we're going to test 100. Since 100 is headed towards the direction of infinity. So if I plug 100 in, look at what the sign gives me. I get a negative in the numerator, negative in the denominator, so 2 negatives makes positive.
How do you know it's continuous? Just state that, or do you have to figure that out?
Okay, so 25 says verify that IVT applies on the interval from 5/2 to 4. So the first thing is we need to establish continuity. And we know that if there's any issues with continuity, it's going to be in the denominator. So let's look to see if there's any issues in the denominator. There is an issue. There's the issue is that x equals 1. That's the only vertical asymptote. That's the only discontinuity in our function. And we just have to look, is that discontinuity going to affect my interval? It does not affect my interval. My function is continuous. I can move on to my next conditions. I'll just go ahead and just finish this problem since we're already on this one. Now, if there was a vertical asymptote, let's say at x equals 3, then if a vertical asymptote impacts or disrupts the interval, then we stop the problem and say function is not continuous, IVT does not apply, and we stop the problem. But the function is continuous, so we have to look at our next options, our next conditions, which is testing our endpoints, plugging in 5/2 and 4 into the original function and looking at their y values. Now, these are a little bit harder to do. This is so the test is without a calculator. I'll give you numbers easier to interpret. I won't give you ones where you're trying to kind of do like messy, calculations. So if I plug 5/2 in for x, I'm going to get roughly 5.8. If I plug 4 in for x of the function, I'm going to get 6.7. I'm looking for a y value of 6. I know my graph is connected. I just need a point, a y value below my target and above my target. If I can see continuity above and below, then I know IVT is going to pass. I know for sure I'm going to have a guaranteed y value of 6 somewhere on the graph between 2.5 and 4. So it says verify that IVT applies. So here's the way that we can write it. By IVT, we've already established continuity, so I don't have to say it again. By IVT, since one endpoint is 35 over 6, which is less than 6, which is less than my upper bound, 20 over 3, coming from f of 4, then we know that f of c equals 6, somewhere on the interval from 2.5 to 4. And then the last thing is find the c value. So we know where the y value is. We know there's a guaranteed order pair that lives between 2.5 and 4. So if I want to find the c value, I'm just replacing my original y value with 6 and then just cross multiplying and trying to solve for x. So this becomes algebraic equation. I cross multiply, bring everything over to one side, factor, and I get 3 and 2. But both 3 and 2 have a y value of 6, but we only care about the x value between 2.5 and 4. So only 3 lands between 2.5 and 4. 2 is outside the interval. So the only c value is 3.
Could you remove full amount? Discuss what it looks like on the graph, like either a whole or a chunk.
Yeah, so do something like this. 4, there's a hole. If the limit exists, but there's a hole, how that if it's non-removable. It can either be an asymptote or it could be a jumpless continuity. Where the limit doesn't exist, and if the limit doesn't exist, it's non-removable.
Can I take a picture? Yeah.
Okay, bell's going to ring in a few minutes. Let me know if you have any other questions.